In this particular problem with vapor pressure, it's a fairly common problem with AP. Now, one of the things that we need to look at here and understand is what exactly does vapor pressure represent? Let's do a quick picture. Okay, in some type of closed system, which could be a container such as a beaker that has a top on it, a bucket with a lid, or even something as large as our classroom, for vapor pressure to be reached, what happens is the liquid turns into a gas, and eventually the gaseous phase becomes saturated with the maximum amount of gaseous particles at that temperature, and some of the gas begins to return to the liquid phase, and we established an equilibrium. For this to occur, there has to be more than sufficient liquid to evaporate and become gaseous, leaving some liquid behind once the vapor pressure is established. Otherwise, we can't have an equilibrium. In the scenario here called A, this would be with the vapor pressure. There's liquid left, the gas has evaporated, it's established a saturated or maximum amount of gas that's present in the volume, and an equilibrium has been reached where as some of the gas turns to liquid, some of the liquid is becoming gas, keeping the amount of gas particles constant. If, on the other hand, as the liquid evaporates, it forms gas, and prior to the equilibrium being established, the liquid phase completely evaporates, this would create a situation in B here where the PVAP is not established because there was insufficient liquid to evaporate to create and reach the vapor pressure at that saturated position where we're in equilibrium between the gas and the liquid phase. Scenario A would represent a situation where we do have the vapor pressure being established inside the container. Now, if we look at our question, it's saying that we have chloroform. 60 grams of chloroform are inside a container that's 20 liters of volume. The vapor pressure of our chloroform is 400 millimeters of mercury. That's the pressure it has when we reach this saturated point of gaseous material that's in equilibrium with the liquid phase. This occurs at a temperature of 43 degrees Celsius. So what we're going to try to figure out is there's sufficient liquid in this container to evaporate, saturate the gaseous space with gaseous chloroform particles and establish an equilibrium reaching the vapor pressure. Or is there insufficient liquid to reach that point? There's several strategies we can utilize to answer this question. The first one, let's take a look at moles. Now here's what we know in our problem. We're given 60 grams of liquid chloroform that are in our container, and our container has a volume of 20 liters. The vapor pressure is 400 millimeters mercury. So we want to figure out, is there sufficient liquid present to establish an equilibrium between the gas and the liquid phases of chloroform. Using moles, we're going to do two things. One, let's find out how many moles of liquid do we have present. And two, how many moles of gas are required to reach the vapor pressure. And we can compare these to see whether or not liquid would remain and if the vapor pressure actually gets established. Our first step, to find moles of liquid chloroform provided, we can use a proportion. We know that 1 mole of chloroform, CHCl3, has a mass of 119.5 grams, which would mean then that X moles of CHCl3 will be present in a sample that's 60 grams in size. Solving for X, we find that we have 0.502 moles of liquid chloroform present in our flask. The second step now is we want to find how many moles of chloroform would be present when we establish the vapor pressure in our flask. For this, we're going to use Pivnert. And what we'll do is solve for the number of moles that would be gaseous at the vapor pressure. Rearranging, we have PV over RT will give us our number of moles that are gaseous. Putting in our information that we have, the vapor pressure of chloroform at 43 degrees is 400 millimeters mercury. To convert that to atmospheres, we're going to do 400 divided by 760. The volume of our container is 20 liters. The R value, 0.0821. Our temperature converted to Kelvin is 316 Kelvin. Calculating this, we find that 0.414 moles of chloroform become gaseous to reach the vapor pressure. Now, because the amount of moles of liquid that's present, 0.502 moles, is greater than 0.414, which is how many moles become gaseous to reach the vapor pressure, that means we have more than sufficient liquid to evaporate and reach the vapor pressure inside this container. The difference between the two numbers would be the excess material that remains liquid and stays liquid because we have an equilibrium between gas and liquid phases, keeping the amount of liquid and the amount of gas constant once we've established the vapor pressure. So because the amount of liquid is greater than the amount of gas that we need to reach the vapor pressure can be established, equilibrium is reached, and a small amount of liquid remains behind in the container during this equilibrium situation. A second strategy or alternative strategy would be to answer this question based on pressure. We know how many moles of liquid we have, 0.502 moles, and we can calculate what would the pressure be in this flask if all of that liquid became gaseous. In this strategy, what we'll do is put the number of moles available in liquid form into Pivnert and say what would the pressure become if all of this liquid became gas. So we have our moles of 0.502, our volume's 20, we have our temperature in Kelvin. When we calculate this, the pressure comes out to 495 millimeters mercury. This is greater than the vapor pressure of 400 millimeters mercury. What this tells us is that there's more than sufficient material present to reach the vapor pressure. Reason being, once we hit 400 millimeters mercury, the pressure cannot go above that because we've reached the saturation point in our container for the maximum amount of gaseous material for this liquid that can exist there at this temperature. So we can never actually get to 495 millimeters mercury because it'll stop at 400. So given that the pressure we would get if all of it evaporated is larger than the vapor pressure, this tells us that some of the liquid would be left behind because the liquid would stop evaporating once we reach 400 millimeters mercury.